Okay, this is Calculus 2.1, rates of change and limits. Now, you guys have all been introduced to limits and rates of change before in pre-calculus, and rates of change really probably back to middle school. Rates of change meaning really just a slope. So, here's a first example. Average versus instantaneous speed. An average speed is just a slope, essentially, between 2 points. So if I talk about this, an average, say I've got a velocity versus time graph. Welcome to physics. Um, we'll be doing a lot of physics applications because calculus uses a lot of physics. So we've got this here, the slope between the 2 points on the velocity time graph is the average rate of change or the average speed or average velocity. Velocity having a direction, so it could be negative, speed does not. And that line here is known as a secant line. We're going to get into something later called a derivative. Here, this is going to be the tangent line. And that is more instantaneous, or your speed at an instant. Okay. So if I'm driving from where I'm at here in Idaho Falls to Boise, and I want to know how long it's going to get there, my average speed becomes very useful, or my secant line. But a cop seeing me going down the highway is more interested in my instantaneous speed. They don't care if my average is only 60 miles per hour if I'm going 120. Okay? They also don't care if my average was 120 if I'm going 80 at that instant. I'm not going to get pulled over as long as it's an 80-mile-an-hour speed limit. Okay. So both have a use, both have a place. So we're going to start with example one over here, which is finding an average speed. Okay. When I find an average speed, I simply do the slope. Why is it not letting me? Why is it changing my zoom? Okay, there we go. So a rock breaks loose from the top of a tall cliff. What is the average speed? So this is section 2.1 on page 55. After it has fallen for 2 seconds. Well, we're given the equation y equals 16t squared. And this is a standard physics equation because it is half the velocity or half the acceleration due to gravity, which acceleration due to gravity in feet per second, you may have heard of it in meters per second being 9.8. Well, in feet per second, it's 32. Not quite as nicely rounded off as 10, but you can get the idea. So I can do a slope formula here. Remember the old slope formula, delta y minus delta x, or change in y over change in x. And you'll see this written like this, called average rate of change. Remember, f of b is just a y coordinate with an x coordinate of b, so y2. So here, I just plug in 16 times 2 squared minus 16 times 0 squared. That's kind of messy. Over 2 minus 0. 2 squared is 4 times 16 is 64. 0 squared is 0 times 16 is 0 over 2 minus 0. So this is 32. An average, this unit is in feet per, our time was 2 seconds. Feet was my distance. Okay, limits. That was not supposed to get drawn. There are a bunch of properties of limits. Now, these might be new, okay? But we've kind of done them. I have not introduced them with this notation in pre-calc. So here, property 1, it's called the sum rule. Limit, okay, there's a couple of actually pieces of information that I should share here. Limit as x approaches c of the function f of x equals L. I don't know why I capitalized the L on limit. Now we're going to do another function g of x, and that's going to equal m. So they're approaching the same point c. Doesn't matter what that point is, it's just c. So the sum rule, I don't know why I'm capitalizing my L on limit. As x approaches c, and this is just as easy as you'd hope it would be. The limit of two functions added together is just add their two limits. That's rule 1. Rule 2 is for subtraction. Same thing. So I can do the limits separately and just add or subtract them. Or multiplication. This is also great. I have f of x times g of x. I can just multiply the two limits. L times n. This next one should be fairly obvious if I have a constant, so say 5 times my function, maybe a function is sine of x. 5 times my function, it's just 5 times that limit. Division. Exactly what you would expect it to be. This will not apply for everything, but for limits, again, you can just divide the limits of the functions. Now there's a little tag here. Because we can't divide by 0. You need to start specifying things like that with as you do this. Now that we're in this high of level math, you have to specify. And rule number 6. Is implying powers. And again, it's exactly as easy as you would hope. They're going to f of x to the power of r over s. So that means this applies to whole number powers and fractional powers being the same as roots. So any version of powers this will apply to. That's an r. Okay? Provided that L to the R over S is a real number. So it doesn't work with necessarily with imaginary numbers. We're just going to be dealing with real numbers here though, so it works out pretty well. So looking at example 3 from the book here. So all of those are here in properties of limits. They're summarized. They're also, I believe, in your packet once you get to the calculus pages. So your formula packet has some calculus pages. So doing these limits, I'm going to make this big for a second. Oh, you can't see this. Never mind. Um, so it has the limit as x approaches c of x cubed plus 4x squared minus 3. And that's very simple. You just take c squared, you plug in, no, not c squared, c cubed. You plug in c for x. And there's your limit. Um, and that works as long as your denominator, oh, this is an example 4, this is still example 3, part B. As long as your denominator is not equal to 0. If your denominator equals 0, then we've got to do some simplifying and try to work it out like we did last year. And we'll do some of those in a second. So the beautiful part about this is I can do these all as separate limits. Using the combination of my rules, oops, that's a plus, not an equals. I can take all of these limits separately, and I would never actually write this notation like this, but that's what I'm doing. I'm checking each one of these to see what it is. So now, these ones, really the limit is x approach. Doesn't matter what x is. This is just 1. This is just 5. Okay. And yes, this really does simplify into c to the 4th plus c squared minus 1 over c squared plus 5. And yeah, if I have a value for c, I'm just plugging it in. Okay. Example 4. limit as x approaches 3 of x squared 2 minus x. I just plug it in. So that is 9 times -1 or -9. My next part of example 4. That's x squared plus 2x plus 4 over x plus 2. Again, I plug in 2. 2 times 2. That's 4 plus 4 plus 4 is 12. Why did I put a 4 there? I'm thinking faster than I can write. 12 over 4 equals 3. You will not get very many of these problems like that. They're too easy. They're fun, funky calculus notation for really middle school math problems. Can you plug in the numbers and work it out? Yes, you can. So, example 5. Tangent of x over x. I'm going to do the limit as x approaches 0. So that's tangent of 0 over 0. Well, I'm dividing by 0. That's a problem. So I'm going to take a look at the graph. And okay, here it is. We're going to look at graphs for a bit. So here I can see, looking at my graph, that this is going towards 1. Okay. Yes, I could do this. And they show it in the book, kind of worked out. Remember that tangent is sine x over cosine x. And that's all over x over 1. When I divide by fractions, I get this. Right. Fraction over a fraction is dividing by the denominator. Because I'm multiplying, you can multiply in any order. You can put things together in fractions. I'm going to say x cosine x. And you can separate the fractions back apart, and then they broke them into 2 separate limits here. This one right here always equals 1. Okay. That is, yes, has a division by 0, and that limit equals 1. I could tell originally that my one from the graph equaled 1 too. They want you to do it by hand. There are 2 known limits in your formula packet. Let me go ahead and open the formula packet and show you those 2 known limits that you get to use. And yeah, one of them was there. So here we get to derivatives, and then over here we get to limits. So it's kind of three, but there's the one I just showed you. There's its reciprocal. This is the other one. Okay. So the sine x over x, right? And I gotta clear these because this is not lined up anymore. So this one turned into the one. Here they just plugged in zero. Cosine of zero happens to be this one here. So 1 times 1 over 1 is 1. We've now shown that algebraically. So you will sometimes get to look at limits and just show them graphically, but a lot of times we have to prove them algebraically. And those couple of limits from the packet prove to be highly useful if you have any trig that you need to show the limit algebraically. Okay, example 6. Again, we're going to use here the book and look at the... So here we've got the limit as x approaches 2 of x cubed minus 1 over x minus 2. If I plug in, I get a zero denominator. So I get 2 cubed minus 1 over 2 minus 2. That's 7 over 0. That is an indeterminate limit. Okay, this is where looking at the graph becomes helpful. If I'm approaching it from the right side, I'm going to infinity. The right side. If I'm approaching it from the left side, I'm going to negative infinity. Those are not the same, so the limit does not exist. Okay, so we would write this one equals dne. The limit does not exist. There you have it. There's your Mean Girls reference. However, one-sided limits almost always exist. And we know, Tatum, it's a little hard to see here. This is the greatest integer function. You've been introduced to that before. It means round down. Remember that 0.5 rounds down to 0. 0.9 also rounds down to 0. Okay? Negative 0.1 rounds down to negative 1. So looking at this greatest integer, it asks me in the problem for limit as x approaches 3 from the right, not an x, it should be a plus, from the right side of the greatest integer of x function. So that one is right here. Where am I going? As I'm coming from the right side of the function, where am I going? 3. However, as I'm coming at it from the left, you're going to get a minus down here. Approaching from the left, as I approach 3, I stay at 2. I don't actually get, it jumps to 3 suddenly, but as I approach 3 from the left, I am at 2. Those are one-sided limits. The two-sided limit, which doesn't have a plus or a minus on the 3, is what, if they're the same, it's whatever that value is. Oops, I forgot the x. We have the x there too. If they're not the same, it does not exist, and we just abbreviate that DNE. Okay? We're going to look at a whole bunch of these on a graph here. So here we've got this graph, and you've looked at some of these in your past, but here we have a graph. And the function below it is all the piecewise functions for those parts, okay? So here we have limit as x approaches 1 from the left. That means where am I going here? From the left, that is 0. From the right approaching 1 is 1. F of 1, the function value is 1. That's where the closed circle is. But the limit as x approaches 1, the two-sided limit, does not exist. So we look at 2. From the left, it goes to 1. From the right, it also goes to 1. So this one, the limit as x approaches 2, is 1, even though f of 2 is 2. So the function value does not have to be there. If the two one-sided limits are going to the same spot, the limit is 1, even though the function value is 2. At 3, well, they're all 2. Going from the left side, the limit as x approaches 3 from the left is 2. From the right is 2. So the limit as x approaches 3, the two-sided limit, is 2. And f of 3 happens to be 2. Um, at x equals 4, we do have f of 4 too, but we just have it approaching from the left side. It does not approach from the right side. The function is not defined there. And our last thing is known as the sandwich theorem or the squish theorem. I kind of like the squish theorem name. This is a pretty famous theorem, and it kind of makes some logical sense if you can understand what they're saying. So this says if g of x is less than f of x is less than h of x. So you can see that in here I have f of x as this crazy weird function. H of x is always larger than f of x, all values. G of x is always smaller. That means my g function is always going to be smaller than my f. My h function will always be larger. And there's some c where the limit for g and the limit for h end up being the same point. It has reference then that the limit of f, if f is squished between g and h, it's going to get squished down. These are the same value, so f has to be that value as well. That's kind of the logic of the theorem. So let's apply it here. Limit as x squared times sine of 1 over x as x approaches 0. It does equal 0. You can see it from the graph. But using the squish theorem, the largest value I can ever get for this is 1. Remember that the sign always oscillates between 1 and -1. So the limit as x approaches 0 of x squared times -1. So that's negative x squared. Negative x squared is always less than my function. See if I can get this advertisement out of my way. Yay. Nope, that didn't work. Oh, there it is. Okay. So my function here in the middle is x squared sine 1 over x. And well, the minimum was negative x squared because sine 1 over x, its minimum is negative 1. My maximum is always positive 1 times x squared. So I've kind of notated this in three distinct limits. Something that's less than the one I'm looking for, what I was asked about, and something that's greater. This gets kind of hard. If you're doing it with sines and cosines, you've got easy maximums and minimums. Sometimes it can get real hard real fast. You will not do advanced ones. And I've posted on Google Classroom a video from Khan Academy that explains this particular theorem really well. So now if I look at my limit, I can just plug in 0. Limit as negative x squared, as x approaches 0 of negative x squared is 0. My one that I'm trying to find, x squared sine 1 over x. And then limit as x approaches 0 of positive x squared is 0. So this is 0 is less than or equal to this thing, and it is less than or equal to 0. That means it has to equal 0. And that is the functionality of the sandwich theorem or squish theorem. And there we have section 2.1.